Welcome. We've previously looked at solving the least squares problem using geometry. In this video, we're going to use an analytical approach using gradients. So objectives are to introduce what we mean by gradients of linear and quadratic functions of w. Then we'll show how to use these gradients to solve the least squares problem, show that the solution we obtain does indeed minimize the squared error, and introduce the idea of projection matrices. So recall the least squares problem involves finding some model parameters w, a p by 1 vector. We want to take a matrix of n features, each of those features being p-dimensional, times the model parameters, subtract off the n labels, and minimize the sum of the squared error between these two terms. The 2 norm of a vector squared can be written as the inner product of that vector with itself. So what we're going to do is expand this squared error out by representing the 2 norm as AW minus D quantity transpose times AW minus D. And one important property that we're going to need to use is the transpose of a product is just the product of the transposes in the reverse order. So when I take the product of AW transpose times AW, I'm going to write that as W transpose A transpose times AW. Similarly, the transpose of AW times D, marked in blue here, is just W transpose A transpose D. And we have D transpose times AW, which gives us this term. And then finally, D transpose times D, which is the last term. And this is our cost function, our squared error, that we want to minimize with respect to W. You can see that this is a quadratic function in the vector W. The term W transpose A transpose D and D transpose A W are both linear. They only involve one term of W. And this first term, W transpose A W, involves W multiplied by itself, so that's going to be a quadratic factor. Now before we go ahead and try to solve this, I want to take you back to a scalar problem and see how we solve that, because that's going to be the pattern that we'll use. So recall, if we minimize with respect to some W, a quadratic function of w, a squared w squared minus 2 beta w plus gamma squared, one way to do that is to differentiate this quadratic function g with respect to w and set that equal to 0. So if we take the derivative with respect to w, we have 2 times a squared w minus 2 beta equals 0, or w is a inverse squared times beta. And since a squared is greater than 0, we know that this quadratic is concave up, and therefore this is a minimum, and that the second derivative is positive. So in order to follow the same approach with our quadratic function of the vector w, what we want to do is differentiate f of w with respect to the vector w and set that equal to 0. Now we're going to define the gradient of f with respect to w as a column vector, and it consists of the partial derivative of f with respect to each variable in w. So the first element is the partial with respect to w1 of f. The second element is the partial with respect to w2 of f, all the way through the pth element, which will be the partial with respect to wp of f. And I've written a transpose up here so that this indeed is a column vector. So let's suppose we have a function which is linear in w. In other words, the inner product of w is some vector h, and I can write that inner product w transpose h or h transpose w. These are identical functions, so the gradient should be identical whichever order I do the inner product. We can write that out as the sum I equals 1 to p wi times hi. So if I look at differentiating this sum with respect to one value of w, say the jth value of w, all the other terms in this sum are going to go away. And when I take the derivative, I'm just going to be left with the jth value of h. So this partial derivative of f with respect to wj is just h sub j. So when I take the partial with respect to w1, I get h1, partial with respect to w2, I get h2, and so on up to hp, and that's just h. Now suppose we have a quadratic term in w where w transpose q times w. And if you were to multiply this out and write it in terms of the individual elements of W, you find that you have W1 squared, W1 times W2, W2 squared, W1 times W3, and so on. If you take the gradient, in other words, the derivative of this function with respect to those individual elements in the W vector, you can show that it's just Q transpose times W plus Q times W. The case that we're interested in, Q is actually symmetric, as we'll show in a minute. And if Q is equal to Q transpose, then this gradient expression simplifies to 2 times Q times W. So this is somewhat reminiscent of the scalar case. When we differentiate a scalar, W squared times some constant, say Q, I get 2 times Q times W. So in our case, we had W transpose A W. So Q is given by A transpose A. And you can check that this is indeed a symmetric matrix, because if I take the transpose of the quantity A transpose A, that's the transpose of the individual terms in reversed order. And I end up exactly where I started. So this is indeed a symmetric matrix. So now that we have these results for the gradient, we can find a solution. We're going to set the gradient with respect to W of our squared error cost function to be 0. And this gives us 2 times A transpose A times W when we differentiate this quadratic term using the result we just showed above. So I have 2 times A transpose A times W. And then when I differentiate these two linear terms, take the gradient with respect to W, remember, it doesn't matter whether it's W transpose times the vector H or H transpose times the vector W. Either way, I get H as the gradient. So here, H is in the role of A transpose D. So I'm going to have an A transpose D for this first term. I'm going to have an A transpose D for the second term. And I'm going to set that equal to 0. Well, this is an easy equation to solve. We can take these two A transpose D terms, move them to the right-hand side, and then multiply by the inverse, assuming it exists, of 2 times A transpose A, and that would give us an expression for W of A transpose A quantity inverse times A transpose D. So we're going to look at some of the attributes of this solution. First of all, recall that A is an n by p matrix. P is less than or equal to n. And as we did in the geometric approach, when we use the orthogonality principle, we're going to assume that the rank of A is equal to P, and therefore that A transpose A is an invertible matrix, and so this solution does indeed exist. Now, if the rank of A is less than P, then we have to take a slightly different approach, and we'll do that later. So second question is, does this solution minimize the cost function and to do that, rewriting this expression that we have for the squared error, which was W transpose A W minus W transpose A transpose D minus D transpose A W plus D transpose D, we can rewrite this in equivalent form that will allow us to easily conclude that this is indeed the minimizer. This is a procedure you may have seen before with scalar equations and called completing the square. And I'm just going to write down the result, and then we'll verify that this is indeed the same expression. So I can rewrite f of W as a perfect square in W. Got W minus something here times A transpose A times W minus the same thing. This is a perfect square in W because these other terms, the D transpose D and the second term, they don't depend on W. So the only place W appears is in this squared term. Now let's verify that this second expression is indeed equivalent to this first expression. To do that, we have to multiply out all the terms in this perfect square and then show that we end up back where we started. Blue is going to be W transpose A transpose A times W, and that indeed gives us this first term. Now let's do some of the other terms. The term in pink, if I take W transpose, then I multiply times A transpose A, and then times on the right A transpose A inverse A transpose D. That gives us this expression in pink down here. The orange term, A transpose A inverse A transpose D, quantity transpose times A transpose A times W, that's going to give us this term that I've written in orange below. And then finally, the fourth product that we have when we multiply this out is this rightmost term times A transpose A times the rightmost term on the other side. And that gives us this expression that I've indicated in green. And then these last two terms that I've written down here, I've just carried down from above. There's a lot of matrix products in here, but this fortunately simplifies. So I can look, and these various terms, I have A transpose A and I have A transpose A inverse. So those two are going to cancel out, and this pink term just becomes W transpose A transpose D. Similarly, in orange, the A transpose A inverse cancels the A transpose A, and I'm left with D transpose A times W. The green term also has an A transpose A inverse canceling an A transpose A, and that becomes D transpose A, quantity A transpose A inverse, A transpose D. So we're really close now, and you can see that if I take this term in green and I combine that with the term that I had in black, those two cancel out, and I'm left with the same expression that I started with. Okay, so we went through this exercise basically to show that I can write f of w in two different ways. I can write it in this way here, or I can equivalently write it in a way that looks more complicated, but turns out will give us some insight. So that's why we're writing it in this more complicated form. What I'm going to do is define z of w to be w minus w0, and in that way I can write this more complicated form for f of w as z transpose of w, A transpose A, z of w, plus d transpose d minus d transpose A, quantity A transpose A inverse, A transpose d. Now the reason that we've written it this way is because now the dependence on w is confined entirely to this first term. And we know that A transpose A is a positive definite matrix. And we've shown this in a previous video. So that means that this quadratic, Z transpose times A transpose A times Z, is always greater than or equal to 0. The only time it equals 0 is when Z is equal to 0. So for Z to be equal to 0, we have to set W equals to W0. So the minimum of f occurs when z equals 0, because any other value of z is going to make f larger because this term is positive. Therefore, my minimum happens when w is equal to w0, or w is exactly the solution we found. Therefore, we conclude that we do indeed get a minimum at this particular choice of w. The minimum value is this term on the right. In other words, when we set this to 0, because z is equal to 0, the minimum value of the cost function, or the squared error, is d transpose d minus d transpose A transpose A quantity inverse, A transpose d. Now there are geometric interpretations for what's happening here in this problem. Recall that the span of the columns of A defines a plane through the origin, and when we're trying to minimize the squared error, what we're doing is we're taking some vector d and we're finding the closest vector in the plane to d. So in this drawing I've shown d hat, which is A times our w at the optimum. That's going to be the vector that's in the plane, which is closest to d. The error has to be orthogonal to the plane. D hat can be written as A times the quantity A transpose A inverse times A transpose D. And this matrix, A times A transpose A quantity inverse A transpose, has shown up a number of times, and we're going to give that a special name. We're going to call that P sub A. So we're writing D hat as P sub A times D. And this matrix P sub A is what we call a projection matrix. Because if I multiply any vector by P sub A, is project that vector onto the span of the columns of A. And you can think about this as having a flashlight, shining the flashlight on D, and the flashlight has to be oriented perpendicular to the plane, and then the shadow of D on the plane represents the projection of D onto the plane. And because the flashlight is perpendicular, that projection is the closest possible vector in the plane to D. Now, one of the very interesting things about projection matrices, if I apply P sub A twice, in other words, I multiply again by P sub A, and it gives me p sub a squared, I really shouldn't change anything because it's already in the plane. And indeed, you can run through the algebra. P sub a squared is p sub a, and you can continue this. P sub a raised to any power is going to be exactly p sub a. Now the error is orthogonal to the space spanned by the columns of A, and we can write that as d minus d hat, vector in pink here. And so if I take d and I subtract d hat, we wrote d hat as p sub a times d. Therefore, E is I minus p sub a times d. And we'll call this a projection p sub a perp, which is short for perpendicular. This ends up being a projection onto the space orthogonal to that spanned by A. Remember, E has to be orthogonal to the span of A, and so this is like taking a flashlight in the plane of A and shining it on D, and what we're going to see is this part that is orthogonal to the plane of A. So P sub A perp, I minus P sub A, projects onto the space perpendicular to the span of A. And we can also check that this matrix, when I square it, is going to give us back the same matrix. So this is also a projection matrix. Now projection matrices, we're going to see these again in a number of other contexts. They play an important role when we think about taking data or vectors and mapping them down into lower dimensional subspaces. Now the Pythagorean theorem is also at play here, even in higher dimensional spaces. This is a two-dimensional triangle, even though it's a three-dimensional drawing, because the vector d hat and d form a plane or a two-dimensional object. And that's true in higher dimensions too. And the Pythagorean theorem says that the length of the squares of the two legs, if I add those, that's going to be equal to the square of the length of the hypotenuse. So I could write that as the magnitude of d squared, the hypotenuse, has to be equal to the 2 norm squared of the leg E plus the 2 norm squared of the leg d hat. And that allows us to solve easily for the length of E, which you already found on the previous slide, but we're doing it here using geometry. We can write this 2 norm of the error as the 2 norm squared of d minus the 2 norm squared of d hat. Well, the 2 norm squared of d is just d transpose d, and then the 2 norm squared of d hat is d transpose p sub a times d, because p sub a squared is equal to p sub a, and therefore we end up with an expression for the length squared of the error, the minimum squared error, as being able to write it as d transpose times I minus p sub a times d. So that's another way to write it, and it follows directly from the Pythagorean theorem applied to this right triangle.